Welcome. We're going to analyze two specific things from the graphs of a couple of polynomial functions. Actually, we'll use the table of values to go with it. So we're going to be looking at what's called the location principle, and then we're going to be looking at the extrema. First, let's look at the location principle. And that is where we're going to determine the consecutive integers of x between which real zeros are located, and we need to do it using a table of values. We're going to take this polynomial here, and I've done a simple graph of it over here. So let's take a look at that. And what I want you to see is that this is where the zeros are. There's one here, and there's one here, and there's one here. And this is -1, -2, -3, and -4, and 1, 2, 3, 4. And then the y values aren't the issue for this here. But what we're looking for is the specific zeros. But we don't want the specific zero number for the location principle. This is where we're looking for the consecutive integers of x between which they're located. So when you look at the bigger picture of this one, that zero is between -3 and -2. This zero is between 0 and 1, and this zero is between 3 and 4. You can see that on the graph. You have to be able to prove it also with a table of values. So when you do y equals and enter 8x cubed and so on the graphing calculator, you get back this graph. But then you need to do the second function and then the graph function with the word table above it, because that will give you the table of values. And we want to use the table for all the values along here, along the x-axis. So we're going to go over here on this side. And if you look at that table of values, it'll give you these numbers. -45, -91, +55, and 81, 35 for 0, a -35 for 1, -81, a -55 at 3, 91 at 4, and 405 at 5. Look for sign changes, y value sign changes. That is the key point of what you do with the table. You're looking for sign changes. I see a sign change right here. I see another sign change here. I see another sign change here. And when I see those sign changes, that means that I now take this and I go to look at the two x values that sign change happens. So come back to the graph over here. And when we're coming up the graph this way, what's happening is that x of -4, you have a certain y value. And -3, you have a y value. And -2, you have a y value. And so on. Well, at when we get to here, right now, all the y values are in the negatives. Once we cross over the line, now they're in the positives. So the y value changes from negative to positive, while the x value goes past the 0. And that's sort of the key point of that. That one goes that way as this one goes this way. And right at this point is where we go from negative to positive. And then coming the other way, when we come down this way, we go from positive to negative. And the same with the last point. So what we're looking for is the fact we've gone from negative to positive here. That's a sign change, negative to positive. Here we go from positive to negative. And then for this one, we go from negative to positive. And so here we have two zeros, or we have the three zeros, and they each have an x and two x values, they're in between. So we're looking for the consecutive integers of x between which the real zeros are located. So we'd say between -3 and -2, and that's this one. Whoops, I put 21 for some reason. Let's fix that. In fact, I was going to write some of that better. Between -3 and -2, 0 and 1, that's this pair. And 3 and 4, and that's this pair. And this is how I want the answer worded for this. You state those consecutive integers. The whole thing hinges upon having the table and recognizing that it's where the signs change for the y's that you go over to the x's and find those consecutive x's where that sign change happens or occurs between. So that's what we're looking for here, sign changes. Let's get all that writing back. That's our key thing. That's for the location principle. Now let's take a look at Extrema. In Extrema, we're looking for the relative maxima and relative minima. That means the high and the low points. So this is a maximum point. But it's only relative because it's only in one area. It's the highest point, and then it changes and comes down. That makes it relative. And then there's a relative minima, which is down here. So I'll put relative in front of both of those. So our goal is to find where those are. Okay? And sometimes we'll find an in-between area, an approximate. So let's take a look here. We're going to find the lowest and the highest points. We're using the same function from above, so we can use the same xy value or xy table. So let me write out these numbers for it. 155, 81, 40, it's 35, then a -35, -81 with the 2, 3 has -55, 4 has 91, and 5 has 405. Okay, so think about what's happening here as we go along the x-axis. The function is going up, it's increasing. It gets to this point and then it starts decreasing. So what we want to see on the y values is it going up and then coming down. Where's the place where it changes? Well, here, from -45 to -91, it's go up to 55, go up to 81, and then it's going down. So what's happening is increases, and then here decreases. That makes this part like the highest point. Now it might be like -1.1 or -0.982 or something like that, but it's still in the table of values, that's the closest. So this relative maximum here is probably that. So what I'm going to say is relative maximum is the point -181. And then we're going to go down to look at the opposite. Look over here at as the x values continue to increase, the function's decreasing, and then it gets to a point where it turns and it goes increasing. So on the graph, we're looking for turns. Look for turns. Okay. But here we're looking for highest and lowest points. That's highest point. And now we're going to look for lowest points. So what I see is it's going down, 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 and then at negative 81 and 2, it turns and starts coming up. So here and here and here, it increases. So that means the relative minimum, I think I'll write that more clearly. Would be this point, 2 and negative 81. That's probably this one that's here on the graph, because that's the lowest y value in the area. Here's the lowest high x value before it turns, and the lowest y value before it turns up. So it's 2 and negative 81, and that's the lowest point. So all of this is, and in particular these two, are the answers to it. Okay, so hopefully now you can see what you're looking for without a graph, but just with a table of values. And in fact, now let's take a look on the next two problems. It's exactly that. We're going to look at doing this only with a table, not with the graph. This is a good time to stop or the video, pause it, do these two problems, and then come back to see if I did also the same way, and check to see if you're right. So pause the video and come on back. All right, you're back now from having worked on those. You put down for this polynomial, for the x and the y's, the table of values shows these numbers if you did them right. Negative 3 and negative 3, negative 2 and 5, negative 1 and 3, 0 and negative 3, 1 and negative 7, 2 and negative 3, 3 and 15, 4 and 53. So now what I see, I do see sign changes here. In fact, it looks like there's a sign change here, and then a sign change here, and another sign change here. So these two x values, I'll do something like that to show, that's where the sign change happens between, and then the same thing with these two, and then the same thing with these two. So that's enough to determine, I'll put stars over here by those, that these are where the real zeros are between. Because it changed sign here, that 0 has to be between negative 3 and negative 2. It might actually be at one of them, but most probably it's between them for this. So the answer would be between negative 3 and negative 2, negative 1 and 0, and 2 and 3. Okay. So that's just it. Use the table of values to identify where the sign changes are. Okay, let me finish getting this up there. Now we're going to do the extrema, the relative maximum and minimum. And it's the same equation, so we put the same numbers down. Negative 27, negative 3, 5, 3 and negative 3, negative 7, negative 3, 15, and 53. This time for maximum minimum, we're only looking for the highest point in an area and the lowest point in an area. So 5 looks like it because going from negative 3 up to 5 and then coming down to from 5 with the 3 after it. So from -3 up and then down from 5 to 3. And then the same thing's going to be true with the minimum point, the -7, going from -3 up to -7 and then coming down away from the -7. That's one way to think of it. So here in this case, what we need is the point that's here. We need -2 and 5, and we need 1 and -7. That's the lowest point, highest point and lowest point when there's a turn. The true highest and lowest points, of course, are infinity and negative infinity. But we're talking about an area where it turns, a smaller spot chosen from the whole overall line. So, so the extrema here, this is the relative maximum, is the relative minimum. Okay. Sure, I matched up my numbers right. Okay. I'm going to make the size of this better. So now what you've looked at is using the table of values to do two different things. It can even be the same table of values, but it's really important to recognize that you can use that to find the consecutive integers of x between which they're located, or to find the relative maximum and relative minimum. There might be more than one. So two of them where I showed on the graph what it looks like, and two of them without a graph, because you don't need one as long as you can make the table, and then look for sign changes or for highest and lowest point. Okay, that's all, and hopefully helps with understanding these two major concepts, important parts of what you need to know for polynomials and their specific graphs and things about them, their characteristics. Thank you for listening and watching. I hope this was helpful.